So I'm gonna be very fast, but it's not really something very deep. It's exactly the same thing. So okay. Do you see what I'm sharing now?
Not really. I think it's wide zoom. Yeah. Okay, it's perfect now.
Okay, now it's okay.
Yeah, it's okay.
So okay, so one of the important properties about mean curvature flow applied to discrete data. Well, till now I didn't talk about discrete data, but there is a way to define it for discrete data. And when we define it like in an approximate way, we see that it helps in denoising images. We can use it as a very good tool to denoise images. So there are some definitions of mean curvature flow for point clouds that were proposed with my supervisor. We are working in a new definition, which is inspired from the Brakke definition. Okay, so I'm gonna go directly to the definition of a point cloud varifold. It's just you take points in this space and you put a tangent at any point, and your measure becomes, and you put some masses at any points, and your measure becomes the sum of masses. Dirac measure at a point, Dirac measure at tangent. So you see the mass, the point, and the tangent. And the mass measure of bifolds is just you ignore the tangential part. Well, so the problem we are investigating is the next Cauchy problem. There is a reason why mean curvature flow for point cloud does not make sense. It just disappear. I'm gonna talk about it later. So we're gonna fix epsilon. We're gonna fix approximation scale, and we're gonna define an approximate mean curvature flow for point cloud. And we're gonna prove some properties when epsilon goes to 0 and when the point cloud converts to a submanifold. Okay, so this is a formal Cauchy problem. The derivative equal h epsilon, and the starting point is any varifold. So we proved that there is a solution, and we constructed this solution. How do we do that? We just take a subdivision of time. You take any varifold, v equals 0. We index our flow by epsilon and delta t. And t. T is a subdivision, epsilon approximation scale. And at each time we do push forward with velocity equal to h epsilon. So you fix a varifold, you do push forward with h epsilon at any time. You compute it again, you do push forward, you do push forward, you do push forward. And it gives you an approximate mean curvature flow for anything you want, including point clouds. And what we want to do is to find the solution of the Cauchy problem, you take the time step to 0 and you fix epsilon. So this is what we've done. Before that, we have a stability property. Two flows, the distance between two flows is bounded by the distance at the time t equals 0 plus the subdivision step, which is delta t. Ignore just the other constant and ignore the epsilon because epsilon is fixed. So this is a stability property needed to prove that the Cauchy problem has a solution. This is a stability. So we have a solution. We fix epsilon, we fix a varifold, any varifold, so any measure. This flow, when the time step goes to 0, converges to a limit. So this gives a solution to the Cauchy problem, and this limit has a stability property. So the distance at any time is bounded by something which depends on epsilon at the distance at time equals 0. Okay, so and this solution satisfies Brakke equality and not inequality. It's a Brakke equality. So you start with any varifold, you can construct an approximate flow with epsilon fixed, and you have the Brakke equality. We forgot about rectifiability because you start with any varifold. You forget, and we have the boundedness of the mass. And in particular, from this equality, you know that the mass is decreasing by just replacing phi by the constant function. Anyway, so we have a solution to the question asked above, how to define mean curvature flow, approximate mean curvature flow for anything. Just discretize the mean curvature. It's just discretize the formal Cauchy problem. Okay, the question now is, for some obvious reasons, the mean curvature of a point cloud, the mean curvature of a point cloud does not exist because like it's dispersed, it's dispersed, and they're not connected to each other. So the mean curvature flow would not make sense. But what if you take mean curvature? What if you take point clouds conversion to? Sorry, I'm just gonna just put the light on. We have point clouds conversion to a submanifold. What can happen? So first, we're gonna replace a Brakke inequality by a integrated Brakke inequality for some technical reasons. Sorry, for some technical reasons. So instead of defining, you take a measure of this form, Vt, you tensor with dt, and instead of defining the mean curvature at a point at time t, you define it for the whole time. Well, I choose 0, 1 just for simplicity. You can choose any time interval. So instead of having the divergence of x, so the change of mass equal to something times the mean curvature, we have the divergence of x, so the differentiation, the derivative of the mass integrated in time equals to something integrated. So this is a mean curvature, which is and can be understood as integral of the mean curvature with respect to time. You don't take mean curvature at time, a fixed time, but you take it for the whole times. These technical things allows us to generalize what Brakke does in the case of rectifiable flows. Okay, so what we got, more or less, the flow we constructed when epsilon goes to 0 has this following property. It admits has this following property, like it decomposes in this way. You have something defined on R, something defined on the Grassmannian, and dt. Because we start with something times dt, at the end we have something times dt. This is more or less what we say, but it's not really that important. What is important is that it admits a space-time mean curvature. So we start with something, we define the formal solution of Cauchy problem, and we tend to the limit. A limit has a nice property, which is admits a space-time mean curvature, and it satisfies the Brakke flow inequality. Okay, so this is okay. This was a definition. Sorry, this is a definition of Brakke flow. What I was saying is that our flow converges to something which satisfies this. So our flow converges to a space-time Brakke flow. Well, I'm gonna we have the avoidance principle. Avoidance principle of what we constructed. If it avoids something at time 0, then it's avoided for any time. What is very important? What is something important that we proved is that if you start with anything which is contained in a surface, its flow will be contained in the evolution of the surface. And this is something was proved by Brakke too, just a slight adaptation, give the reasons for different measures. What else we proved? So there is a triviality issue. This is the last result. There is a triviality issue that Brakke encounter, is that sometimes the flows of Brakke is trivial, and people later on proved that in some cases the Brakke is trivial, and some other cases Brakke is not trivial, and some people gave it a characterization. What is the characterization? Is that if you have endpoints, if you don't have any volume inside, your flow gonna disappear because the endpoints has some singular mean curvature that's gonna push your object to a point and your object is gonna disappear. So what we proved is just a generalization of what some people proved, that if you have something inside your variable, this this will allow, sorry, if you have a volume inside your variable, you cannot disappear instantly. You have to evolve in a continuous way. Okay. Here's how how we formulate the theorem. If you start with a variable that is a boundary of an open set of finite parameters, let's say, to simplify, if you start with a variable which is a C2 manifold, assume it's compact. Okay, so C2 manifold, compact C2 manifold. You consider this formal solution to the Cauchy problem. When you take epsilon to 0, the limit is something not non-trivial, because you have something inside, you have a volume inside you that's gonna control your evolution. This was proved for Brakke in the set of Brakke flow, and the same proof works fine for space-time Brakke flows, which are Brakke flows where we have a mean curvature which doesn't see the object at time t, but see the whole evolution. This is more or less what we done. Thank you for your attention.